Welcome. This is 48C video 2, and we're going to do the second part of this chapter, and the second part of the chapter is to do with free fall. Free fall occurs when a body is only acted on by gravity. So if I have an object that's falling because gravity is pulling on it, and I have air resistance, that's not free fall, because the air resistance is an additional force. If I have a body which is falling in the absence of air resistance, that would be free fall. If I have an object that is in my hand, that's not in free fall. If I have an object that has hit the ground, that is not in free fall. Here's the catch. If I have an object that I have thrown upwards, even though it's going upwards, it's in free fall. If the object is stationary at the top of its motion, it's still in free fall. And if the object is falling downwards in the absence of air resistance, it's still in free fall. So we tend to talk in these free fall motion projects about objects like, for instance, a diver jumping off a diving board and falling into the water, or somebody stepping off a cliff, etc. Things like that. And the trick is, we don't concern ourselves with air resistance, and we don't concern ourselves with how the body acted while it was touching, say, the board or the roof or the ground before the journey began, and we don't concern ourselves with how the body behaves once it touches the water or the floor or whatever at the end of the journey. We only can apply kinematic equations when the object is in free fall, and that is when it's not touching anything. So what we say is, if we disregard air resistance, all objects fall towards the earth with the same acceleration. That in itself is a little bit strange. If you think about it, a heavy object versus a light object. Big weight, small weight. We know enough to know that F equals ma. Big weight would imply big acceleration. But what we see is A is equal to F over m. So if the big weight is caused by a big mass, then the mass is bigger and the two effects cancel. So big objects, small objects, they all experience the same acceleration due to gravity. So that's very interesting. And then the second thing we say is a free falling body is an object moving under the influence of gravity only, regardless of its initial motion. Objects thrown upwards or downwards, or those released from rest, are all falling freely once they are released. So if I have a diver and the diver jumps upwards, as soon as it leaves the board, it's in free fall. If the diver just steps off the board, as soon as he or she leaves the board, they're in free fall. And if a diver was to grab hold of the board and pull themselves downwards with a big initial velocity, once they leave the board, they are still in free fall, because free fall is about having only gravity act on you, so you have the acceleration due to gravity. And once they are free to fall, all objects have the same acceleration downwards, pointing downwards, equal to the acceleration due to gravity. It's 9.8. We prefer 10 meters per second squared. We say it's negative to indicate that it's pointing downwards. Now, the velocity can be upwards even if the acceleration is downwards. That's slowing down on the way up. The velocity can be zero even if the acceleration is downwards. That's when you're at the top of the journey. And the velocity can be downwards while the acceleration is downwards, and that's when you're falling towards Earth. So let's try one of these. What you notice is that the question tells you a lot less. It's got fewer words in it. A diver. steps off a diving board. The board is 5 meters above the water, so that distance from there to there is 5 meters. And the diver steps off the diving board. The diver has 3 choices. The diver can jump upwards, the diver can step off, or the diver can pull themselves physically downwards. And in this case, the diver has chosen to step off the diving board. How long does it take her to reach the water? So if that's the start of my journey and that's the end of my journey, I'd like to know my duration, my delta t. Okay. So let's think what I know. I want delta t, so let's put that down. And then, oh yeah, of course, I know that the acceleration due to gravity in all these problems will be minus 10 meters per second squared, minus because it's pointing downwards. And then, the diver steps off the diving board. That's code for the initial equals 0 meters per second. If the diver had jumped upwards, the initial would be positive, maybe 5, maybe 10 meters per second. If the diver had pulled themselves downwards, then it would be a negative initial velocity, maybe 5, maybe 10 meters per second. But because the diver simply stepped sideways off the board, they had no upwards velocity, no downwards velocity, so their initial velocity is 0. It does not say that in the words, it's implied. This is where you have to build visualization. And we know that our displacement goes from the beginning of the journey towards the end. So our displacement is not just 5 meters. 5 meters implies positive 5 meters. That's not true. We didn't go upwards. We went downwards. So our displacement is minus 5 meters. That's critical. If you have just put 5 in, you'll get a implication is a positive value and your equations will be different. Thinking about equations, what equation is going to link these things? Let's have a look. Delta x is equal to vi delta t plus 1/2 a delta t squared. So minus 5 is equal to 0 times delta t plus 1/2 times minus 10 times delta t squared. So minus 5 is equal to minus 5 delta t squared. Delta t squared is equal to minus 5 over minus 5, which equals plus 1. Delta t is equal to the square root of 1, which equals plus or minus 1. Clearly, if I start my clock at the beginning, my duration would be delta t equals plus 1 second. It's a good thing to remember, actually. When you drop an object, it falls 5 meters in the first second. 15 feet roughly. 5 meters in the first second. So there we have it. So let's do a second question. A softball player throws a ball vertically upwards into the air. There's my V initial. The ball takes 5 seconds to reach its maximum height. Delta t equals 5 seconds. With what velocity was the ball thrown? Okay. So there's the start of my journey. And here's the end as far as my calculation's concerned. So let's make a list. The list says VI equals, I don't know. A, of course, is always equal to minus 10 meters per second squared in a free fall problem. My duration, my time interval, I'm told is equal to 5 seconds. And what else do I know? Oh yes. It's not given, but I know the final velocity. If I end my journey at the top, my final velocity is equal to 0 meters per second. What equation do I use? I say Vf is equal to Vi plus A delta t. 0 is equal to Vi plus A minus 10 times delta t, which is 5. So 0 is equal to Vi plus minus 50. So that means that Vi is equal to plus 50 meters per second. Notice that plus sign means that the velocity was pointing upwards, which is what we'd expect. So that makes sense. Let's do a third example. A diver jumps off a high board with a velocity of plus 12 meters per second. Let's call this Vi. The high board is 6 meters above the water. What is her velocity as she reaches the water? So let's visualize the journey, and I'd like to know her velocity, there's V final, as she reaches the water. So let's say that this is the end of my journey and this is the start of my journey. And let's see what I know. I know my Vi for this journey is plus 12 meters per second. I know that my acceleration for this journey is minus 10 meters per second squared. I know that my displacement for this journey is equal to, let's be careful, we go from the beginning to the end, the start to the finish. So it's going to equal minus 6 meters, and I want to find my final velocity. So I say Vf squared equals Vi squared plus 2a delta x, and we substitute in what we know. Well, Vf squared I don't know, but I do know Vi squared. It's plus 12 squared plus 2 times minus 10 times minus 6. So Vf squared is equal to 144 plus 2 times minus 10 is minus 20 times minus 6 is plus 120. So Vf squared is equal to 264. So Vf is equal to the square root of 264. Vf is equal to, get my calculator, second square root 264 equals plus or minus 16.25 meters per second. Mathematically, I suppose I could leave it like that, but physically I know the difference between the positive and the negative, and I look at my diagram, and clearly the correct answer is VF is equal to minus 16.25 meters per second. And at this stage, at this level, of course, you are expected to be able to get the sign right as well as the numerical value right. So 3 examples. You can see there are 1,000 examples I could give you. I could give you off a diving board. I could have stepping off, jumping down. I could have you jumping up off the ground and coming back down again. I could have you jumping onto a mesa or a desk. I could have you jumping from a tall building to a short building, or a short building to a tall building. I could have you jumping in various places. It's various things I can do. So practice, 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 and don't expect to see exactly the same problem, because you won't see the same problem again. Thank you.